One of the most important techniques that you developed in Calc 1 and Calc 2 was the idea of U substitution. So this is really just the chain rule for integrals. Just to remind you, if we have an integral of e to the 3x dx, here we could make the substitution u equals 3x. And you could solve this for x, so x is u over 3. And then take differentials, we get dx is 1/3 du. Then we could plug these back into the integral and get e to the u times 1/3 du. So really this just gave us e to the u du, and then we had this integrating factor in here, this 1/3. So in general, what's going to happen here is we've got u equals g of x. Then we take the inverse, so x is g inverse of u. Then taking differentials here, we've got dx equals the derivative of g inverse of u times du. And then we'll plug this back into the integral. And this integrating factor right here is what we want to focus on when we do this technique for double and triple integrals. So let's look at a double integral. Let's say, I'm going to look at the general theory first, and then we'll look at a more concrete example. Let's say we're taking a double integral over some region, and just for emphasis, this region is given in terms of x, y coordinates, and this area is in terms of x and y. Well, the idea here is we're going to do a substitution, although instead of just being a regular u sub, you can think of this sort of like a double substitution, a double u sub, where we're gonna do some substitution. U is a function of x and y, and v is some function of x and y. So we have sort of two substitutions going on here at once. So what's going to happen is first the region of integration, our limits, will change. So it'll be some new region in terms of u and v. The integrand will change also, because x is now a function of u and v. So what we'll do is we'll get rid of the x and replace it in terms of u's and v's. And the same with the y. We'll replace y in terms of u and v. And then we pick up this integration factor, sort of akin to what we had back in the 1D case. And then this will be in terms of u and v as far as the area goes. Now this integrating factor right here, the shorthand we have for this is the derivative of the old variables with respect to the new variables. This symbol right here is called the J for the Jacobian of that transformation. So what does this mean right here, the partial of the old variables with respect to the new variables? Well, in the case of u, v, and x and y, this is the partial of the old variables, which is x and y, with respect to the new variables, which in this case is u and v. And this gives us a matrix. This is the partial of x with respect to u, partial of x with respect to v. So the top row are their x partials, the bottom row are the y partials. And this is partial of y with respect to u and the partial of y with respect to v. Now u and v are just sort of placeholders in this. We may have other variables other than u and v that make more sense to plug in, but the theory behind this is the same. Let's look at an example that we would usually use polar for, but we'll actually go through the Jacobian process on. Let's look at the integral of square root of 9 minus x squared minus y squared, where the region is the disk of radius 2 centered at the origin. So this is sort of like a classic polar problem, because the region we're integrating over is a disk, and the function looks like it would go well with polar. So this is sort of a classic polar integral. So our region of integration is the disk of radius 2, everything inside the circle of radius 2. So that means for the range and the thetas, if we look at our theta first and our r, the thetas, we take on the full circle's worth of values. So theta is going from 0 to 2 pi. And the r's are going from the center of the circle, r equals 0, out to the edge, which is the radius, which in this case is 2. So our r is going from 0 to 2. That says we can trade in this double integral in x and y for this iterated integral, theta goes from 0 to 2 pi, r goes from 0 to 2. Now our function, well, we have the substitution x equals r cosine theta, y equals r sine theta. So we replace all the x's with r cosine theta, we replace all the y's with r sine theta, and we can do some trig identities here and reduce this to the square root of 9 minus r squared. Next up comes the Jacobian. So if we look at this 2 by 2 matrix here, our new variables are not u and v, but they're r and theta. So our Jacobian here is going to be the determinant of the partial of the old variables with respect to the new variables. So the partial of x with respect to r, partial of x with respect to theta, and the partial of y with respect to r, partial of y with respect to theta. So if we evaluate those derivatives, the partial of, now here are the functions that we have. The partial of x with respect to r is cosine theta. The partial of x with respect to theta is negative r sine theta. And then the bottom row, the y partials. The partial of y with respect to r is sine theta. And the partial of y with respect to theta is r cosine theta. So now we go through and evaluate this determinant. And we cross multiply here, we've got r cosine squared theta minus negative r sine squared theta. We can factor the r out here, and we've got cosine squared plus sine squared, which is 1, so that gives us r for our Jacobian. So, and that's that r factor that we saw coming up in polar coordinates all the time. It's just the Jacobian of the transformation. So we've got our Jacobian in there, and then r is range going from 0 to 2, and theta from 0 to 2 pi. So that's the gist of the Jacobian in 2 variables. In 3 variables, it's the same idea. If we've got a triple integral over some region in x, y, and z of a function of x, y, and z, this we can trade in for some new region. And again, the x we just write in terms of u, v, and w, whatever the new variables are here. Y in terms of u, v, and w. Z in terms of u, v, and w. And we have this Jacobian in here. And this Jacobian is the partial of, again, it's the partial of the old variables with respect to the new variables. So, and this just gives us the determinant of a 3 by 3 matrix. In this case, where we have x, y, z, u, v, w, this is the partial of x with respect to u, x with respect to v, x with respect to w. Then our second row are the y partials, and the bottom row are the z partials. So using this definition right here, it's a good exercise. You have to use a bunch of trig identities for this. Show that the Jacobian in cylindrical coordinates is r, and show that the Jacobian for spherical coordinates is rho squared sine phi. I'll give you some good practice for Jacobians. Let's look at one slightly less standard example. Let's go through and find the volume of the ellipsoid, and we'll give the general ellipsoid formula: x minus h squared over a squared, y minus k squared over b squared, and z minus l squared over c squared equals 1. So the volume of the ellipsoid, now remember our volume is just the triple integral of dv. Now if we were going to actually set this up as is, we would probably have a trig sub, actually more than one trig sub on this, which says we've got to do some sort of change of variables on here. Now we can't use polar or cylindrical because this is not a circle. So we've got to do some other sort of change of variables, and that leads us to the Jacobian. So let's first figure out what the u, v, and w are. So I guess I should say on here, it's everything inside the ellipsoid. So this looks sort of like a square plus a square plus a square is less than or equal to 1. So if I choose this quantity right here to be my u squared, then u equals x minus h over a, v equals y minus k over b, and w equals z minus l over c. What that does for the region, that says this ellipsoid in terms of u, v, and w, well, this is just u squared. So this is u squared plus v squared plus w squared is less than or equal to 1. And this is actually the unit sphere, or the unit ball. So that is, says if we do this change of coordinates, we could then use spherical after the fact, because now we have an actual sphere for our region of integration. So that says that let's do this substitution then. So that means we're going to have this right here over the unit ball. That's going to be our new region of integration. Now, when we change over into this UVW coordinates, we're going to have this Jacobian and then dV. So let's figure out what the Jacobian is. First, in order to get the Jacobian, remember this is the derivative of the old variables with respect to the new ones. So we need to take this system of equations right here and solve for the old variables. So if we take this first equation, solve this for x, we get that this is au plus h. For the y equation, we solve this for y. We get that this is bv plus k. And the last one, we solve for z, and we get that this is cw plus l. So our Jacobian now, this will be the determinant. So the first row are the x partials. The partial of x with respect to u is a. The other partials of x are both 0, because x does not depend on either v or w. So next up are the y partials. The partial of y with respect to u is 0. Partial of y with respect to v is b. Partial of y with respect to w is 0. And then the z partials go the same way. The partial of z with respect to u is 0. Partial of z with respect to v is 0. Partial of z with respect to w is c. This is a triangular matrix. In fact, this is diagonal. So the Jacobian here is just going to be the product of the diagonals, which is ABC. So that gives us, for this is the triple integral over the unit ball of the Jacobian ABC times dV. Now, A, B, and C are all constants. They were the length of the semi-axes. So this constant you can bring right out of the integral times the triple integral over the unit ball dV. And this right here is just the volume of the unit ball, and we have a formula for that. Remember, the formula for volume is 4/3 pi r cubed, and the radius in this case is 1. So this will give us ABC times 4/3 pi. So that is the volume of this general ellipsoid. So we can see that Jacobians let us evaluate some integrals that would normally be impossible without.